Okay, you're going to hear me more than you'll see me here because I'm going to go through a second Newton's Law of Motion lab that's focused on net force equals mass times acceleration, which in terms of doing a lab is actually quite challenging because of the prevalence of forces such as friction, that every time you try and drag something around, kind of get in the way of isolating how much force is actually acting on an object. So what you're looking at is a device that we use in physics that is called an air track. Now I'll step in view here so I can show you kind of how it works. The idea with an air track is there is this triangular arm that's hollow, and then in this box on the one end there is actually a blower. And this functions kind of like a hockey air track in that when it's on, along this triangular hollowed arm, there are all these little holes that are drilled in there. So when this gets turned on, they push out puffs of air. And then there are specially shaped carts that you can set on the air track so that when you turn the air track on, this rides on a cushion of air, and essentially it reduces or eliminates essentially all of the friction that this would encounter as it would move right or left. Now it's quite loud, and so that is why I'm just going to turn it on, show you how it works, and then we'll set up the lab and do a couple runs here. So we flip the switch and it gets loud. And you'll notice that it doesn't look like this thing is moving very much, but if I push it, I got a piece of tape on this other side that I got to fold under. There we go. Let's try this again. You can see that this cart will just bounce back and forth, and it glides, frictionlessly on the arm. So we can get rid of friction through the use of the air track. So if we turn this off, you can see that at a certain point the air doesn't come out and we encounter friction again and this stops. Now, how are we going to make use of this to do a net law lab activity? I'm going to put a cart on the air track, and on the far end here where I'm presently located, there is a little arm that has a pulley wheel on it. And what we can do is we can hang a mass on the end of the string that hangs from the pulley wheel. And if we turn the air track on, what will happen is when we let go, and I'm going to step out of the way of this, you'll notice that come around to this side, that as the mass over here is pulled to the ground by gravity, it will drag the cart across the air track. And you'll notice that it picks up speed as it does so because it's undergoing an acceleration. So our force that drives this whole thing is simply the weight of this mass hanging on the end, and then we have our system that is going to undergo an acceleration. Now what we have to be able to do is we have to be able to take some measurements off of this so that we could collect some data and see, does Newton's law actually work here? Now in order to do that, what we are going to make use of are these things that are called, let me get this here, which way are we doing this? They are referred to as photo gates. And the photo gates they're like invisible eye markers that when the cart passes, get this over here, when the cart passes through a particular spot, it trips a beam, and that starts a timer. Now our timer is contained, and you're having to watch the entire process happen here. Our timer is contained within this laptop because we're going to make use of a special kind of a device called a Vernier photo gate setup, so that when the cart trips one of the photo gates, it will start a timer on the software, and when it trips the other photo gate by blocking it when it goes through, it will stop it. So that will allow us to figure out how much time does it take to go between these two photo gates. Now the one thing that I have pre-planned is I have already set up where, have some pieces of tape here, so I'm going to position the photo gates so that I know that they are a set distance apart from each other because I've already measured that with a meter stick. So we're going to see if we can open up our software here, and we're going to have to set up our photo gates, and then we're going to do a couple runs, and then in a follow-up video I'm going to show you the data that we collect off of this and give you numbers. And then what we're going to look at is you can do a theoretical calculation based on if we know the mass of the cart and the mass of this hanging object, and we know how far apart our measuring spots are, we can theoretically figure out what the acceleration of this system should be. And then what we're going to do is, since we know how far our photo gates are apart, we're going to do our best to start it from 0, because I'm going to release this very carefully here. We can measure how much time does it take to get between the two photo gates, and from that data we can calculate an experimental acceleration, and then we're going to compare our theoretical acceleration to our experimental acceleration, see what our percent error is between the two. Okay, so what I got to do here is I got to very carefully move this thing around until the photo gate is just where I want it. All right, we got it there. Now, what we want to do is we want to bring it right here. I'm sure this is like super exciting to watch. And then what I'm going to do is I'm going to give you, we're going to try and do this maybe 2 or 3 times. And I'm going to say the data, and I'm going to have to explain exactly how this thing keeps time. Let's see. All right, I think we're good there. The way this system works is that when I start the timer, it starts a stopwatch. And then I am going to let go of the cart and it will accelerate through here. Now the timer is already going to be running, so the first time that this is going to record is an actual time. So I'm going to say that time out, and then when it stops this photo gate, it stops that timer. So we will have a start time and a finish time, and what we'll have to do when we go to process the data is actually subtract the two. So this is going to get a little loud, and I'm going to try and say the numbers out nice and loudly. And then we'll try, let's say 3 times. And then we'll use that as our collected data. So here we go. Alright, so our beginning time was 11.945434, and our stop time is 13.516026. Okay? This is one of the challenging aspects of this lab, is that setting it up just right can be a little bit of a challenge. Hold on. Okay. Start time is 11.369738. Stop time is 12.944718. Okay, we're going to try this one more time. Okay, the start time is 9.577218, and the stop time is 11.146662. Okay, so now we can turn this off. We can bring this back in here. So what we've collected are three trials of times that it takes to go 81 centimeters. So I'm going to stop this, and what we're going to be doing is creating another video where we'll go into the whiteboard and we'll talk about how do you process the initial measurements of the pieces so that you can figure out what's the theoretical acceleration, and then how do you process the actual data that we collected so that you can see what your experimental acceleration is. We'll see how close they are to each other. All right? So we'll see you on the next one.